Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, today we will start the module 6, and in this module we are going to study regarding the parametrically excited systems. So, already you are familiar with the system. So, where we have taken, so for example, you just take this cantilever beam which is subjected to an excitation force here. So, if it is subjected to an excitation force, so in this case the forcing, and so you can note the forcing. So, you are applying this force here. So, the forcing and the displacement take in the same direction, forcing and displacement, forcing and the displacement takes in the same direction. Second example, you just take of the spring mass damper system also, or spring mass system. Here also if you are applying a force in this direction, that is f sin omega t. So, here the displacement is also taking place in the same direction. But let us take another example where we have a column. In this column, so let us apply a force in this vertical direction. So, let us apply this buckling force, that is instead of a constant force P, let us apply a force P0 plus P1 cos omega t. So, let us apply a periodic force. You can see that, so in this column, so already you know regarding the Euler buckling load. So, in static case, so if you are applying a force, constant force, then when it exceeds the Euler buckling load, so then it will start to buckle, cantilever beam will start to buckle, but at this end there will be 0 slope. Okay, so there will be 0 slope up to certain range you have seen. So, in case of the Euler buckling load, when we are applying a constant load to the column, so it starts to buckle. So, in this case the displacement takes in a direction, so perpendicular to the direction of application of force. So, here you are applying force in one direction and the displacement is taking place in the other direction. So, let us take in this cantilever beam also. So, if we are applying a load, for example, in this horizontal direction, that is P equal to P0 plus P1 cos omega t, you can see that if you are applying a force in this horizontal direction, so it will start to buckle or start to bend after for certain value of P1 and omega, which is very less than that of its critical load. Similarly, in this case also, much below this critical Euler buckling load, the beam starts to buckle. So, depending on the value of P0, P1 and omega, for depending on the value of this P1, that is the amplitude of the periodic part, and omega is the frequency of the periodic part. So, depending on this P1 and omega, we can observe that the beam starts to buckle at very less value in comparison to the critical Euler buckling load. If you can plot these, sometimes you may plot this P1 for a particular value of a P0. So, if you can plot this P1 versus this omega, so you can see or you can get certain curve like this, where you can tell beam will buckle. For example, let us take the value of P1, this is the value of P1. So, in this case you can see, so this is stable, so this is unstable and this is stable again. So, for this value of omega, the system remain stable. So, there will be no buckling of the system. Similarly, for value greater than this, so there will be no buckling and the system will be stable, but in this range the system is unstable and in this range the column starts to buckle. So, we have to find different value of a P 1 and omega for which it will start to buckle. So, this type of excitation, when we are applying a force in one direction and displacement is taking in a perpendicular direction, are known as parametrically excited system. So, these are known as parametrically excited system. So, in the previous case, so you have given the direct excitation. So, direct excitation, the forcing and the displacements are taking place in the same direction. So, this is the direct loading. This is also in case of cantilever beam, when you have applied a force in transverse direction and the displacement is taking place in transverse direction. So, that is you are giving a direct loading, but if you are giving a loading in one direction and displacement is taking in a perpendicular direction. So, that time the system is known as parametrically excited system. So, already you have derived the equation of similar system, where for example, you might have, you can recall the system what we have taken. So, that of a pendulum. So, let this is a pendulum where the platform is moving, up and down direction. So, if the platform is moving, so in this case, so you can get a equation of that of a parametrically excited system. Here the force is applied in this vertical direction and the displacement is taking, so in this horizontal direction. This is a case of a parametrically excited system. So, you can actually apply this parametrically excited system in many applications. For example, for plucking of these fruits in the from the tree. So, you can shake the tree or you can shake the branch of the tree in one direction, but the fruits can be coming down due to the vibration in a direction perpendicular to that of the direction in which you are applying this force. So, there are many such applications are there. You can take a base excited. So, for example, this is a base excited cantilever beam. So, this is a beam cantilever beam and this is a shaker. So, the shaker is developed. So, we have developed the shaker in house. So, this is the oscilloscope. So, you can see we did some experiment and the response is periodic, or so we have put some piezoelectric patch also here. So, you can see some piezoelectric patch are put on the beam, and so when this beam is moving up and down, or when the shaker is given a force in upward direction, so it moves in the transverse direction. So, due to this transverse direction movement of the beam, so the piezoelectric patch gets strained and due to that thing this voltage is generated. So, if you take this voltage, then you can see the voltage from the oscilloscope. This type of oscillations are known as parametrically oscillation in a parametrically excited systems. So, in this type of systems you can see in the previous case, here the equation of motion can be written in this form, that is x double dot plus k x plus c x dot equal to f sin omega t. So, this forcing part you can see can be represented in the right hand side of this equation, and in case of the parametrically excited system, the equation can be written in this form. This is x double dot plus k x plus, so you can write this is equal to p t into x. So, plus if you want to add a damping term, so then you can put for example 2, or you can write this c, you can write equal to c x dot, c x dot. So, that will be equal to 0. So, in this case it will be equal to 0. The equation, so here you can note or you can see that the response term x, the coefficient of the response term here k is constant, but this part. So, in this case this is a time varying term. So, this p t is a time varying term. So, if the coefficient of this x is a parameter, and that is why this is known as a parametrically excited system. So, here p t, which is a parameter and is written as the coefficient of the response of the system, and that is why this type of systems are known as parametrically excited system. In this parametrically excited system, generally the equation can be written in this form, that is u double dot plus p 1 t u dot plus p 2 t u equal to 0, where this p 1 and p 2 are time varying term. As the time varying terms are coefficient of the response and its derivative, this equation is called the equation of a parametrically excited system. You can write this type of equation, and this type of equation can be conveniently reduced to some other forms. For example, if you take u equal to x e to the power minus half integration p 1 t dt. So, you can eliminate this damping term, or you can eliminate this u dot term. So, here by putting this u equal to x e to the power minus half integration p 1 t dt, then you can find, or you can write this equation in this form, that is x double dot plus p t x equal to 0, where p t equal to p 2 minus 1 by 4 p 1 square minus half p 1 dot. This equation where, so now you have reduced this p 1 t u dot term is not there, that is the derivative term is not there, and it is simply written by x double dot plus p t into x. So, there is no u dot term here or x dot term here in this equation. So, this equation is known as Hill's equation. If you take this p t equal to delta plus 2 epsilon cos 2 t, then this equation can be written x double dot plus delta x plus 2 epsilon cos 2 t x equal to 0. This equation is known as Matthew equation. This equation is the Hill's equation, and the second equation what just now I told, that is x double dot plus delta x plus 2 epsilon cos 2 t x equal to 0. Here the periodic term, that is 2 epsilon cos 2 t is the coefficient of x. So, that is why this is a equation of a parametrically excited system. So, unlike in case of force vibration or direct excitation, you know that the resonance will occur at a frequency when the excitation frequency is equal to the natural frequency of the system. For example, in case of a single spring mass system, so you have seen, so when the natural frequency is equal to the, or when the excitation frequency is equal to the natural frequency, you have observed the resonance conditions. If you recall this magnification factor, so magnification factor versus this omega by omega n, where omega is the external frequency and omega n is the natural frequency. So, for undamped system, so the response will be like this. So, at omega equal to omega n, so that is at value 1, at omega equal to omega n. So, the resonance, it is the resonance condition, or the response tends to infinite. By applying this damping, so this can be reduced, the amplitude can be reduced. So, that is, so this is your zeta equal to 0, that is damping equal to 0. So, you can put some certain value of damping and you can have a relation like this, or response like this. But in case of the parametrically excited systems, you can observe that when the frequency, external frequency is away from the natural frequency, then you have the resonance condition. For example, so you can have when omega equal to omega m plus omega n, so you can have the resonance condition. So, what is m and n? So, m and n are the, so for example, m equal to 1, n equal to also 1. So, this becomes 2. So, when m equal to 1 and n equal to 1, this omega equal to 2 omega 1. So, omega equal to 2 omega 1. In that case, it is known as principal parametric resonance condition of the first mode. We have taken m equal to 1, n equal to 1, that means the first mode we are taking. That means when the system is oscillating at its first mode, then the resonance will occur when this external frequency is twice that of the natural frequency. If we are considering twice the second natural frequency, then it will be principal parametric resonance of second mode. Similarly, principal parametric resonance of third mode, that way we can write the principal parametric resonance. So, when m not equal to n, so in that case we will have combination parametric resonance. For example, m equal to 1, n equal to 2. So, in that case we will have the combination parametric resonance of the first and second mode of some type. We can have some or difference type also. So, we may have a minus sign here also. So, taking m equal to 2 and n equal to 1. So, we will have omega equal to omega 2 minus omega 1. So, in that case we will have combination parametric resonance of difference type. In this case you have seen when the frequency is away from the natural frequency, then we are getting the resonance condition. Particularly we are finding the resonance condition when it is twice the natural frequency, those are known as principal parametric resonance condition, and when it is combination of different modes also. So, it may be some type or difference type. So, combination resonance of some type and combination resonance of difference type. So, three different type of resonance conditions you have observed here. One is principal parametric resonance condition, second one is combination parametric resonance condition of some type, and third one is combination parametric resonance of difference type. All those resonance conditions we will see in next classes. Another example you just see where we can get or where we can find this type of equation also. For example, we are solving, when we are solving this doping equation, and to solve this doping equation already we know. So, we can use different methods. For example, previously we have used method of multiple scales, and we have used this method of Lindstedt-Poincare technique also harmonic balance method, method of averaging, and different perturbation methods we have used. For example, while we have used this method of multiple scales, so in that case we got the reduced equation. By perturbing those reduced equations, we got the Jacobian matrix, and by finding the eigenvalue of the Jacobian matrix we studied the stability. But if we are going to use, for example, use this harmonic balance method. So, if we are going to use harmonic balance method, in this case, for example, let us take this harmonic balance method where we assume the solution to be u equal to u0 equal to a1 cos omega t plus b1 sin omega t plus a3 cos 3 omega t plus b3 sin 3 omega t. Now, by substituting this equation in this original equation and then separating the coefficient of cos omega t, sin omega t, cos 3 omega t and sin 3 omega t, we got a matrix of A and B. By solving that matrix, we can get the coefficient A1 B1 and A3 B3, and we know the solution u equal to u0. So, in that case we can get this u0. So, the solution we got or the equilibrium state we got. To study that equilibrium point, so whether that equilibrium point is stable or not, so we have to perturb this equation, this original equation we have to perturb around the equilibrium position u0. We can take this u equal to u0 plus u1, where u1 is the perturbation over this u0. We can write u equal to u0 plus u1 in the first equation, and you just note that as u0 is the equilibrium solution. So, it will directly satisfy this first equation. We can write this equation after substituting it in this equation. So, we can write this equation in this form. So, it will be u1 double dot plus omega 0 square u1 plus 2 epsilon mu u1 dot plus 3 epsilon alpha a1 cos omega t plus b1 sin omega t plus a3 cos omega 3 t plus b3 sin omega 3 t square into u1. You just see, so this is nothing but this is u0, this is the expression for u0, and it is a function of u0. So, at the nonlinear term, this u cube nonlinear term is present here. You can have this term here in this perturbation. That means, if you have expanding this thing by substituting u equal to u0 plus u1 in this epsilon alpha. So, for example, epsilon alpha u cube. So, you can write this equal to epsilon alpha then this becomes u0 cube plus u1 cube plus 3 u0 square u1 plus 3 u0 u1 square. So, this way you can write, you can expand this thing and you can see. So, this term actually it will go when you are substituting this u equal to u0 in this original equation. So, if you substitute u equal to u0 in this original equation, so your equation becomes u0 double dot plus omega 0 square u0 plus 2 epsilon mu u0 dot plus epsilon alpha u0 cube. So, this will be equal to k cos omega t. Now, when we are substituting this u equal to u0 plus u1, so it has to satisfy this equation as u0 is the equilibrium solution, and neglecting this term as u1 is very small. So, u1 square can be neglected. So, you just see this term is already here, epsilon u0 cube, this k cos omega t and k cos omega t will cancel. The remaining terms will be this, where you can write this equation in this form, and this can be reduced, or it can be reduced in this following form also, that is u1 double dot plus omega 0 square u1 plus 2 epsilon mu u1 dot plus. So, this whole term, these are time varying term. So, that thing I can put equal to epsilon ft. So, epsilon ft into u1. So, as u1 is, so this is epsilon term. So, 3 alpha into this u0 square can be written as ft. So, this equation can be written in this form. So, here you just note, or you can see that this equation is written u1 double dot plus omega 0 square u1, where omega 0 is the frequency, natural frequency of the system, plus 2 epsilon u 2 epsilon mu u dot. So, this is the damping term, plus you have a forcing term or epsilon ft u1, where this ft, this time varying term, is the coefficient of u1, which is the response of the system. So, this equation is reduced to that of a Matthew-Hill type of equation. So, now what you have seen while studying the stability of the doping equation. So, if you are not using the method like this method of multiple scale or the averaging method, so where directly you are getting this equilibrium solution and the stability, but if you are using some method like this harmonic balance method, then after getting the solution you must have to perturb the original equation to study its stability about the equilibrium position. So, here the equilibrium position is u0. Now, you have perturbed this u0, or you have given a perturbation of u1 about u0. So, that you have written this u equal to u0 plus u1, and you have landed with this equation, which is similar to that of a Matthew-Hill type of equation. So, by solving this equation, so you can know what is the solution of this thing. So, if the solution, if the response is growing, that means if u1 is growing with time, then the systems becomes unstable, and if it is remaining within certain limit, certain bound, then the response is bounded or the response is stable. So, we can study. So, there are different methods to study the stability, or different methods are there to study this type of system. Here also we can use this perturbation methods also to study the response of the system, and also to find the parametric instability region and study the system behavior. Let us see one theory. So, this is the Floquet theory, which is generally used to study the stability of such type of system. So, here you have seen as the system content. So, this is the coefficient is periodic. So, we are expecting to get the periodic solution out of this equation. So, let us see. So, let us consider the system u double dot plus p1 t u dot plus p2 t u equal to 0. Since this equation is a linear second order differential equation, so in this case there must exist, and this is a homogeneous differential equation, right hand side equal to 0. At the second order it must contain, or there exist two two linear non-zero independent fundamental sets of solution in this case. So, we have two fundamental sets of solution. So, for example, let us take this u1t and u2t are the two fundamental set of solutions. Now, we can write this ut equal to, as these are fundamental set of solutions. So, a combination of linear combination of these two solutions are also a solution. So, we can write this ut equal to c1 u1t plus c2 u2t. So, we are assuming here this p1t and p2t are periodic function of time. So, if they are periodic function of time, that means p1t equal to p1t plus t, where t is the time period. So, this t is the time period. So, after one period this value must be same. So, if we are assuming this p1t and p2t, so I can write this pit also. So, I equal to 1 and 2. So, I equal to 1 and 2. So, pit equal to pit plus t. So, in that case, so I can write this equation u double dot. Now, substituting, so after one cycle let us see, so what will be the response. So, then we can replace this t by t plus t. So, t plus capital T is the time period. So, then u double dot t plus t can be written. So, in this original equation we are substituting t equal to t plus t. So, we are replacing this t by t plus t. So, to check what will happen after one cycle. So, u double dot t plus t will be equal to, we have taken these two terms to the right hand side, that is why it will be minus p1 t plus t and u dot t plus t minus p2 t plus t into u t plus t. So, already you know that p1 t plus t equal to p1 t and p2 t plus t equal to p2 t. So, in this case, so we can write this equation equal to minus p1 t u dot t plus t plus p2 t u t plus t. So, you just compare this original equation with this equation, they are same. So, here you can observe that this, if ut is a solution, so ut plus t is also a solution of the system. So, here what you have taken, so you have taken two fundamental set of solution, that is u1t and u2t, and you have now observed that if ut is a solution, then ut plus t is also a solution of the system. So, as ut plus t is solution, hence if u1t and u2t are fundamental set of solutions of that equation, then u1t plus t and u2t plus t are also fundamental set of solution of that equation. So, if u1t plus t and u2t plus t are fundamental set of solution, we can write this equal to a11 u1t plus a12 u2t, and then ut plus t can be written as a21 u1t plus a22 u2t, or you can write this thing also. So, for example, so you can write this u1 t plus t and u2 t plus t, this vector can be written in this matrix form also. So, this will be a11, a12, a21, a22 into u1, u1t and u2t. Clearly, you just observe that this u1 and u2 are determined after one cycle. Starting from t, for example, t equal to 0, we can find what is the response at after one cycle. Then knowing that response, we can write down this u t plus t and u2 t plus t as a matrix A. So, this is a matrix A. So, this is a non-singular matrix, you can take this Aij or element of a constant non-singular matrix A. So, starting with this u1t and u2t with some initial condition. So, we can find what is the response after one cycle. So, knowing that response, we can write down this in this form, and then we can find. So, this matrix is, you just see this matrix is not unique and it depends on the fundamental sets being used. We can use different set of this u1, u2, and we can have different sets of A for finding this response. We can choose this U1 and U2 in such way that we can get this A matrix diagonal, then this equation will be uncoupled. For example, so if this A12 and A21 are 0, then we can write this U1 t plus t will be equal to A11 U1 t, and U2 t plus t will be equal to A22 U2 t. As these are not unique, so we can get another set of U1 U2 or another set of fundamental solutions for which these diagonal it will be A will be a diagonal matrix or the off diagonal terms will be 0. We will have only the diagonal matrix, these off diagonal terms will be 0. Let us name them as V1 and V2. So, then V1 and V2 we can write in this way. So, V1 t plus t equal to A11 V1 t. So, we can write this as lambda 1 V1 t also. So, then V2 t plus t we can write this is equal to A22 V2 t, or we can write this as lambda 2 V2 t. That means, we can get a set of solution for which the A matrix will be only diagonal. These off diagonal terms are 0, and in that case we can write this V1 t1 plus t equal to lambda 1 V1 t and V2 t plus t equal to lambda 2 V2 t. So, here this lambda is a constant which may be complex also. So, these solutions are known as the normal or Floquet solution. The set of solution for which the A matrix is diagonal are known as Floquet solution or normal solution. So, in that case we can write this V I t plus t equal to lambda I V I t. So, I equal to 1 and 2 we can substitute, so that we can have this V1 t plus t equal to lambda 1 V1 t and V2 t plus t equal to lambda 2 V2 t plus t. Now, let us add one more cycle. So, for example, we will so this V, now you have seen this, for example, let us take only V1. So, V1 t plus t. So, you have seen V1 t plus t equal to lambda 1 V1 t. Now, if I will add one more cycle, for example, I will write this V t plus t plus t, another t let me add. So, then this becomes what? So, then this becomes t plus 2t. So, this is nothing but V1 t plus 2t. So, in that case what I will write? So, I can write this equal to, this thing can be written as V1. So, it is V1 t plus t plus t. So, this is equal to so, as already you know V1 t plus t equal to V1 t plus t equal to lambda 1 V1 t. You can write, so for the first case it will be lambda 1 V1 t, and then again you have to multiply. So, this thing Vi t plus 2t can be written as Vi t plus t plus t. So, this is written as lambda I, this part you can write equal to, conveniently you can write this as lambda I. For example, let us you take this part as t dash. So, this t plus t equal to t dash. So, Vi t dash plus t will be nothing but lambda I Vi t dash. So, this part we have written t dash, so that you will not get confused. So, Vi t plus t can be written as Vi t plus t plus t. So, this t plus t if I am putting as t dash. So, you know Vi t dash plus t will be equal to lambda I Vi t dash. Again you just see this Vi t dash is nothing but Vi t plus t. So, in that case it will again reduce to lambda I Vi t. So, in this way you are getting lambda I square Vi t. Here Vi t plus 2t equal to lambda I square Vi t. Similarly, if you take Vi t plus nt, n times time period, after n time period if you want to find what should be the response. So, in that case it can be written as lambda I to the power n Vi t. So, lambda I to the power n Vi t. In this way, so you can write this Vi t plus nt equal to lambda I to the power n Vi t. Here n is the integer 1, 2, 3, 4, n will be 2, 3, 4. So, that we have seen. So, t plus 2t, t plus 2t, here we have lambda square, and nt. So, it will have lambda to the power n. Here what we have seen for steady state, as t tends to time t tends to infinite. So, n should tends to infinite also. So, that means, so if we are writing for example this V I t plus n t, so this is equal to lambda to the power n V I t. So, you have seen this equation. So, here, so for steady state, that is t tends to infinite. So, how t will tends to infinite? So, when this n t tends to infinite, t will tends to infinite, or this n tends to infinite, this becomes an infinite. So, implies n tends to infinite. So, you just see if n tends to infinite, here you just see lambda to the power n. So, we have this lambda to the power n V I t, it must be. So, for steady state, so we can write this V I t equal to 0. So, V I t will be equal to 1 by lambda V I t, you can write, though that is for steady state. So, that time we will write this in terms of t. So, it will be, so this side you just see, so V I t can be written as lambda to the power n V I t, this is the V I initial t 0 I can put, or I can write, let me write this way. So, V I t will be equal to lambda to the power n. So, starting from V I t 0, so to avoid confusion, so you just write the starting point is t 0. So, after t tends to infinite, that is n tends to infinite. So, you can write this way, if this lambda I mod lambda I less than 1. So, if mod lambda I less than 1, so in that case you just see this V I t will tends to 0. If lambda I, that means if you have a fraction, so less than 1 means, so you have a fraction. So, if you have a fraction, so for example, let us take 1 by 2, 1 by 2 to the power infinite. So, 2 to the power infinite. So, 1 by 2 to the power infinite, so it tends to 0. V I t will be 0, that means the response will comes to the trivial state, that is 0. So, if lambda I less than 1 means this lambda I is a fraction. So, if it is a fraction only, so in that case as t tends to infinite, the response also tends to this 0, and if it is greater than 1. So, you just see if lambda greater than 1, then for example, let us take 2. So, 2 to the power infinite will tends to infinite. The response will be unbounded, that is the response will be unstable, or the system will be unstable. So, if this lambda I mod lambda I greater than 1, we can draw, that means we can draw a circle, unit circle. So, we can draw a unit circle, and in this unit circle, so this is 1. So, we can draw a unit circle. So, for example, this lambda is a complex number. So, we can have the real part and imaginary part. So, we can draw this unit circle, and if the roots or the lambda are inside this unit circle, then the system is stable. So, if it is outside the unit circle, then the system is unstable. So, from here we have understood that this lambda must be less than 1, or it must lie within this unit circle, so that the system will be stable. So, when lambda I equal to 1, so V I, so you can see when lambda I equal to 1, so V I t is periodic with period t, and if lambda I equal to minus 1, V I is periodic with period 2t. So, that thing you can observe from here. So, because we are writing this V I t plus t, V I t plus t equal to lambda V I t. So, from this thing, or n t, so if you add n t, so from this thing you can see this. So, if lambda equal to 1, so for example, lambda equal to 1, so V I t plus t equal to V I t. So, it has a period t. So, now if let us take this lambda equal to minus 1, so V I t plus t plus t. So, if we are taking this lambda equal to minus 1, so it will be equal to this if we are putting this n. So, let us put this n t. So, V I plus n t. So, you just see for n equal to 2 only, so this will becomes V I t. So, for n equal to 2, so for n equal to 2 V I t plus So, NT we are taking. So, 2T will be equal to VIT. So, that is why if lambda equal to minus 1. So, you can see if lambda I equal to minus 1, then Vi is periodic with period 2T. So, here you have seen this Vi if lambda I equal to minus 1, then the system has a 2 periodic. So, it is a 2 periodic system. So, it must have a period 2T depending on the lambda value. From this equation or from this equation you can decide. So, what is the least value of lambda for which this will be periodic or 2 periodic. These form the basic of the bifurcation analysis for periodic response. So, later we will study the stability of the periodic solution. So, in that case we will see different type of bifurcation. Actually this lambda equal to 1 form the transition curve. So, it forms the transition. So, below, so from stable to unstable region. So, later we will see. So, if the roots or the lambda that they are roots of the monodromy matrix also later we will see. So, if they are coming out of this region, so either it can come to this point, it can come through this point, or it can come as a complex conjugate. So, depending on these things, so we will have different bifurcation, and those bifurcations we will study in next few classes. So, the system is stable if lambda is remain within the unit circle and are unstable if they are outside the unit circle. On the boundary of the unit circle, the solution may be periodic or 2 periodic depending on the positive or negative value of lambda I. So, depending on the negative or positive value of, so if it is positive, so if it is positive then it is periodic, and if it is negative, if lambda I is negative then it is of 2 periodic depending on the positive and negative value of lambda I. We can, instead of using lambda, so we can use another, we can write it in another form also. Now, let us multiply this e to the power minus gamma I t plus t in this equation V I t plus t equal to lambda I V I t. So, both the side if you multiply this minus gamma e to the power minus gamma I t plus t, then we can see e to the power minus t plus t V I t plus t equal to lambda I. So, previously we have this lambda I, lambda. So, you just see the previously you have this lambda I V I t. So, now you have multiplied this by e to the power minus gamma I t. So, this becomes lambda I e to the power minus gamma I t into e to the power minus gamma I t V I t e to the power. So, you can write this e to the power minus gamma I t plus t equal to e to the power minus gamma I t into e to the power minus gamma I capital T. Now, expanding, so you have expanded this in the right hand side. So, you have written this lambda I e to the power minus gamma I t and e to the power minus gamma I t V I t. So, now what we can do? So, we can choose this lambda I in such way that this lambda I equal to e to the power gamma I t. So, if we can write this lambda I equal to e to the power gamma I t, now what you can see? So, lambda I we have written e to the power gamma I t, and so here also we have another term that is e to the power minus gamma I t. So, we can multiply these two which will give rise to 1. So, this is e to the power, the remaining thing is e to the power minus gamma I t into V I t. This lambda I by taking these things, so we can write in this form. So, but you just note this e to the power minus gamma I t plus t. So, what we have observed here, e to the power minus gamma I t plus t into V I t plus t is nothing but e to the power minus gamma I t into V I t. This term we can write as phi I t also. If this is V 1 t is a solution, so then and V 1 t and V 2 are two solution, then this multiplication of this e to the power minus gamma I t V I t, which can be written as phi I t, will also be a solution, and this. So, from this you can write this V I t equal to phi I into e to the power gamma I t. So, V1t can be written as e to the power gamma 1t into phi 1t, and V2t can be written as e to the power gamma 2t phi 2t. So, where we can write, so from this thing easily we can write this phi I t plus t as V I t plus t equal to V I t. So, we can write this phi I t plus t equal to phi I t also, this way also. So, phi I t, phi I equal to e to the power minus gamma I t V I t is a periodic function with period t. So, we can take this as a periodic function with period t, where from this equation, so lambda I as lambda I we have taken equal to e to the power gamma I t. This implies this gamma I t equal to ln lambda I. So, from this thing, so we can write this gamma I equal to 1 by t ln lambda I. So, this is known as the Floquet multiplier. You can find this Floquet multiplier also. So, gamma I equal to 1 by t ln lambda I. You know that this lambda I must be within this unit circle to make the system stable. So, for this purpose you just see this ln lambda I. So, if it is, we can have different value of this lambda and we can see. So, corresponding to lambda I greater than 1. So, if it is greater than 1, so in that case gamma I is positive, and if lambda I is less than 1, then gamma I is negative. So, if it is point, for example, let us take it is point 1, 0.2 for lambda I. So, then this becomes negative, gamma I is negative, and if we are taking a value greater than 1, then it is positive. By checking whether this gamma I is positive or negative, so we can tell the system is stable or not. So, for a stable system, so gamma I must be negative, because for that system this lambda I must be within this unit circle. When lambda is within this unit circle, so gamma I is negative. Now, in this way, either by checking this lambda I or by checking this Floquet multiplier gamma I, you can study the stability of a system. This way you can use this Floquet theory to study the stability of a periodic system. So, let us take one example. So, this is an example which also you can find in my NPTEL course. So, in this example, let us use this Floquet theory to study the stability of the following system. So, let us take u double dot plus p1 t u dot plus p2 t u equal to 0. So, these initial conditions are given to us, that is u1 0 equal to 1, u1 dot 0 equal to 0, and u2 0 equal to 0, and u2 dot 0 equal to 1. These are the initial condition known to us. So, what is u1 and u2? So, u1 and u2 are two fundamental sets of solution for this equation, and after one cycle, so we have been given that u1 t equal to 4, u1 dot t, u1 dot. So, all these things will be equal to t, u1 dot t equal to 0.5, u2 t equal to 0.5. So, after one cycle, so the values are given to us. What we can do? So, we can write. So, already we know this equation u1 t plus t, u1 t plus t, and u2 t plus t. So, we can write. So, these equal to a11, a12, a21, a22 into this is u1 and u2, u1 t t0 and u2 t0. We can write, for example, in this case. So, all the things have been given to us. So, u1 t plus t, u2 t plus t, we are writing in this way, and from this we can find. So, by differentiating these equations also we can write down this equation again, and from that thing, so we can find what is a1, a2, gamma 1, gamma 2. So, you just see we have 4 unknown. So, a11, a12, a21, a22. So, we required 4 parameters. So, we have taken 2 parameter u1 t, u2 t, and another 2 parameter we can take u1 dot t and u2 dot t, and from that thing we can find this equation. So, the solution, so we can write this way u1 t plus t equal to a11 ut, a12 u2 t, u2 t plus t equal to u1 t plus u 2 to u2 t. Similarly, u1 dot t plus t equal to u11 u1 dot t plus a12 u2 dot t, and this u2 dot t plus t equal to a21 u dot t plus a22 u2 dot t. So, you just see 4 equation, 4 unknowns. So, by solving this thing we can find this. So, by solving this, so we can find, for example, let us take u1 t plus t after one cycle. So, u1 value is given to be 4. So, 4 equal to, so you can write in this case. So, your equation becomes 4 equal to a11. So, u1 t, so u1 t is given to be at t equal to 0. So, u1 value equal to 1. So, you can put this is equal to 1. So, a1 into 1. So, plus a12 into u2t. So, you just note that u2t equal to u2t 0 at t equal to 0. So, this is equal to 0. So, I can put equal to 0, a2 into 0. Let us write it here. So, we have u1 t 0 equal to u1 t 0 equal to 1, u1 dot t 0 we have to write equal to u2 t 0, already we have seen this is equal to 0, and u2 dot t 0. So, these values are given. So, let us substitute it here. So, from this thing we have seen u1 dot 0 equal to 0, u2 0 equal to 0, and u2 0. So, u2 0 equal to 0 and this is equal to 1, u2 dot equal to 1, and u1 dot is also given to be, u1 dot is also given to be 1, and these other values are u1 t equal to 4 and u2 t equal to 2. So, let us now write the second equation. So, in second equation 2 equal to u2. So, 2 will be equal to a21 into u1 t equal to 1. So, a21 it becomes, and plus a22 into u2t equal to 0. So, it is multiplied by 0. So, from this thing, so what you have observed? So, you observed that a11 is nothing but it is equal to 4 and a21 equal to 2, or in other words, so you can write this way also, a11 equal to u1 t and a21 equal to u2 t, a12 equal to u1 dot t and a22 equal to u2 dot t. So, this way you can, similarly another 2 equations you can write, and from that thing also you can find the value and you can write this A matrix. So, A equal to u1 t, u1 dot t, u2 t and u2 dot t. So, after finding this A matrix, now you can find, so now A minus lambda I. So, you have to find this lambda. So, A minus lambda I, so you just write determinant of A minus lambda I equal to 0. Now, you can get this thing. So, that means lambda square minus 2 alpha lambda plus delta I equal to 0. So, in this form you can write. So, where alpha equal to, you just see where alpha equal to half u1 t plus u2 dot t and delta equal to u1 t u2 t minus u1 dot t and u2 dot t. So, this is the determinant and this is the trace of that matrix. That way you can write also, or directly from this thing. So, writing this A, after writing this A matrix, determinant of A minus lambda I, you can do determinant of A minus lambda I equal to 0, put determinant of A minus lambda I equal to 0. Otherwise, you can directly find the eigenvalues of A matrix also. So, from that thing you can get this lambda. In this case, for the given parameter, so delta is known as the Wronskian determinant and of u1 and u2 t. So, in the present case, alpha equal to 3, delta equal to 2 minus 1, that is equal to 1, and hence, so lambda square minus 6 lambda plus 1 equal to 0. Hence, lambda you can get, so 2 value of lambda you have got. So, 1 lambda equal to 5.828 and 0.1715. So, you just see as one of the value, that is 5.828 is outside the unit circle, the system is unstable. So, you have seen the system is unstable as one value of lambda is outside the unit circle. So, this way you can use this Floquet multiplier, and in this way you can use this Floquet theory to determine this lambda to find the response of the system. So, instead of finding this lambda value, we can find the Floquet multiplier gamma also, and you can study the stability. So, tomorrow class or next class we are going to use this Floquet multiplier to study the other different system stability of other different systems. Also we will study different other methods to find the instability region. So, here you just see, so we have to find the value of the system parameter for which it is the system is moving from a stable state to unstable state. So, this will give rise to a boundary, and so it will give rise to a boundary for different system parameter. For example, in this case for epsilon and omega, if you want to plot, so you can get a boundary. So, this boundary is known as parametric instability boundary or transition curve. This curve is also known as the transition curve, and we can find the minimum value. So, for example, here you can find the minimum value of epsilon for which the system is always stable. So, this way we can study different boundary or different transition curve for different equations of parametrically excited system. Next class we will take the Hill's equation and find the Hill's determinant also. Also we will use this method of multiple scale and other different methods to find the parametric instability region. Further we will use different continuous systems and we will try to reduce those continuous system to that of a single degree of freedom system and multi degrees of freedom system to find the parametric instability region and the response of the system. Thank you.